Hello everyone, welcome back to our YouTube channel. Today we are back with another topic, that is flow behavior of sheet metal forming. So first of all, material flow behavior. Considerable insight about the behavior of metals during forming can be obtained from the stress-strain curve. The typical stress-strain curve for most metals is divided into an elastic region and a plastic region. In metal forming, the plastic region is of primary interest because the material is plastically and permanently deformed in these processes. The typical stress-strain relationship for a metal exhibits elasticity below the yield point and strain hardening above it. This figures true strain-strain and true stress-strain on log-log scale indicates this behavior in linear and logarithmic axes. In the plastic region, the metal's behavior is expressed by the flow curve. Sigma is equals to K epsilon n, where K is the strength coefficient MPa, as a unit is MPa, and n is the strain hardening exponent. The stress and strain in the flow curve are true stress and true strain. The flow curve is generally valued as a relationship that defines a metal's plastic behavior in cold working. Thank you. Next to Tapas.
Thank you. Next is flow stress. The flow curve describes the stress-strain relationship in the region in which metal forming takes place. It indicates the flow stress of the metal, the strength property that determines forces and power required to accomplish a particular forming operation. For most metals at room temperature, the stress-strain plot indicates that as the metal is deformed, its strength increases due to strain hardening. The stress required to continue deformation must be increased to match this increase in strength. Flow stress is defined as the instantaneous value of stress required to continue deforming the material to keep the metal flowing. It is the yield strength of the metal as a function of strain, which can be expressed in YF is equal to K epsilon n, where YF is equal to flow stress megapascal. So thank you. Over to next.
Now I am going to tell you about average flow stress. The average flow stress, also called the mean flow stress, is the average value of the stress over the stress-strain curve from the beginning of strain to final value that occurs during deformation. The average flow stress is determined by integrating the flow curve equation between 0 and the final strain value, defining the range of the interest. This yields the equation YF equals K into epsilon to the power n whole divided by 1 plus n, where YF equals average flow stresses in megapascal and E equals maximum strain value during the deformation process. Over to next.
Thank you, Akash. So I am going to speak about the temperature in metal forming. The flow curve is a valid representation of stress-strain behavior of a metal during plastic deformation, particularly for cold working operations. For any metal, the values of K and N depend on temperature. Both strength and strain hardening are reduced at higher temperatures. In addition, ductility is increased at higher temperatures. These changes are important because any deformation operation can be accomplished with lower forces and power at elevated temperature. There are three ranges: cold, warm, and hot working. Cold working. Cold working, also known as cold forming, is a metal forming performed at room temperature or slightly above. Significant advantages of cold forming compared to hot working are better accuracy, meaning closer tolerances, better surface finish, strain hardening increases strength and hardness of the part, grain flow during deformation provides the opportunity for desirable directional properties to be obtained in the resulting product, and no heating of the work is required, which saves on furnace and fuel costs and permits higher production rates to be achieved. Owing to this combination of advantages, many cold, close tolerances and good surfaces minimizing the amount of machining required and permitting these operations to be classified as net shape or near net shape processes. There are certain disadvantages or limitations associated with cold forming operations. Higher forces and power are required to perform the operation. Care must be taken to ensure that the surfaces of the starting workpiece are free of scale and dirt. Ductility and strain hardening of the work metal limit the amount of forming that can be done to the part. In some operations, the metal must be annealed in order to allow further deformation to be accomplished. In other cases, the metal is simply not ductile enough to be cold worked. To overcome the strain hardening problem and reduce force and power requirements, many forming operations are performed at elevated temperatures. There are two elevated temperature ranges giving rise to the terms warm working and hot working. Over to next.
Now we will discuss about work working. Because plastic deformation properties are normally enhanced by increasing workpiece temperature, forming operations are sometimes performed at temperatures somewhat above room temperature but below the recrystallization temperature. The term warm working is applied to the second temperature range. The dividing line between cold working and warm working is often expressed in terms of melting point of the metal. The dividing line is usually taken to be 0.3 Tm, where Tm is the melting point or absolute temperature for the particular metal. The lower strength and strain hardening as well as higher ductility of the metal at the intermediate temperatures provide warm working with the following advantages over cold working. First is lower forces and power. Then its more intricate work geometrics are possible and need for annealing may be reduced or eliminated. Thank you. That's all from our side. Please like, share and subscribe to our YouTube channel. Thank you.